In this video and my next couple of videos that I'm making here, we're going to be solving triangles and specifically right triangles, okay? And so when we talk about solving triangles, what we really mean is that we want to find all of the unknown measurements in this triangle. So I think that it's best if we just kind of look at an example to begin with, and I'll cover some basic conventions that we use when we talk about solving triangles, okay? So how about we just start with this in the first place. When it comes to solving triangles, okay, and we want, let's see here, I can get my font a little bit bigger. There we go. Solving triangles. Okay, what we're trying to do is find all angle measurements. We want to find, move my cord here. Find all side lengths. And so when somebody says, go and solve this triangle, essentially all they're saying is that we're going to be doing this. And I just wanted to point that out before we begin because people get intimidated when we say, go solve the triangle. Well, what does that mean? Go find out what you know about it, okay? So when it comes to solving triangles, let's make one thing really clear. In this video, we're discussing only a right triangle. We're talking about right triangle ABC, okay? So it seems that we want to solve when given two angles and a side length. It says solve triangle ABC where A is 40 degrees and C is 12 centimeters, and we want to find all unknowns, okay? So the two pieces of advice I'm going to give anybody when it comes to solving triangles are, first of all, sketch a situation, sketch the triangle, okay? And in this case, we know that we have a right triangle, so we could have some right triangle here, ABC, and we're going to make sure that we make the right angle explicit here, and we're going to label the vertices of this. Now the vertices are these corner points here which our angles are formed, and we tend to, it doesn't have to be, but we tend to label triangles like ABC or TUV or something like that, but like ABC, and we tend to write C as the 90-degree angle or the largest of the three angles. It doesn't have to be that way, but we also tend to write side lengths as lowercase letters instead of the uppercase letters. So for instance here, if this is uppercase C representing that vertex there, then we say then the length of this side is lowercase c. Or if this is vertex A, this angle over here, then we say the length of the side opposite of segment BC is lowercase a, and then we have lowercase b here, okay? So the first thing we want to do is always draw a picture of this and fill in what we know. And in this instance, it seems that we were told that A is 40 degrees, so we would want to go place that on the triangle immediately, and that C is 12 centimeters, okay? So right off the bat, we've been given a situation where we know that we have some right triangle here. And I know I've labeled the sides, but we have a right angle, we have a 40-degree angle, and we have a 12 centimeter side length. So now we can kind of work with this right here. Now the next best thing I can give you advice to do is this. Make a data organizer on the left here. We do this with like law sines, law cosines, but it's good to get in the habit of starting to do this now. And we are going to fill in also what we know. So C, we see C is the right angle here. So we say C is 90 degrees. We know that lowercase c is 12 centimeters, so we're going to put that into our graphic organizer here as well. And then we say angle A is 40 degrees. Okay, so now let's start with this. We were given a task, and that task was to go ahead and find all of the unknown things we know about this triangle. And I want you to consider this in terms of the things that I'm missing, that I don't know yet. Which of them would probably be the easiest to solve for first? Think about this. You might pause the video. In terms of what I want to solve for one of the two unknown side lengths or the angle, I think that it's most convenient to solve for the angle. And the reason why is because all the angles in a right triangle must sum to 180 degrees. So what we know is this. If we were to add up all three angles, we should get a 180-degree answer, okay? Another thing I want to point out about right triangles is this. If all the angles add up to 90 degrees and 90 of those degrees are right there, then what this means is that this angle right here and this angle right here, these also add up to 90. We have a special name for this. We say they are complementary angles, okay? And so the reason why I point this out is because we already knew that angle A is 40 degrees. So if angle A is 40 degrees, really we're asking ourselves this question now, what could I add on to angle B to get it to add up to 90 degrees total, okay? So here's how we'll write this. We know that the measure of angle A plus the measure of angle B has to be 90 degrees. And we're already aware that angle A is 40 degrees. So if we were to say 40 degrees plus, I'm just going to write it as B, is equal to 90 degrees, the question really becomes, well, then what is the measure of angle B? And we can find this just by subtracting 40 degrees from both sides. So when you're given two angles in any triangle, not just a right triangle, you can always find the third angle by using the fact that all angles add up to 180 degrees. So we have all three of our angles now. Now the question becomes, what are the lengths A and B here. Okay, and so this is where SOHCAHTOA is going to come in handy. Now I would love to use the Pythagorean theorem. It is a right triangle, but you'll notice here that there are two side lengths that I don't know instead of just one side length that I don't know. And so that's going to make using Pythagoras a little bit difficult here. So we're going to use SOHCAHTOA. And this is usable when working with right triangles, okay? So we can use SOHCAHTOA when we're dealing with right triangles. I just want to make sure that we got that note down. So if that's the case, let's take a look at what we have here. The question becomes, what is A? Okay, so maybe I want to solve for A. The question now is, what trig ratio could I use, sine, cosine, or tangent, that would relate A, which is what I don't know, to two things that I do know? And for instance, in this case, we could say, well, I know that A is 40 degrees, angle A, and I know that side length C is 12 centimeters. Could I use those pieces of information to determine what the length of side A is? And in this case, what we'll do is we'll use sine. Okay, so if we said sine, why would I want to use sine? And the reason behind this is because sine is opposite over hypotenuse. So what this allows us to do is take this angle here that we know and rewrite this as the sine of 40 degrees is equal to opposite over hypotenuse, and you'll notice that our opposite side here has a length of A and that our hypotenuse has a length of 12 centimeters. Okay, so now the question becomes, well, what is A? And we could find this if we were to take both sides times this 12 centimeters right here. We would be able to find the length of A because those would cancel out and we're left with this. A equals 12 of these sines of 40 degrees, and this is in centimeters, okay? So this is where we would get our calculators out. This isn't a hard thing to do. We would say, all right, well, I want to take sine of 40 degrees. So I notice I'm in degrees. I say 40. We'll take the sine of that. So here's my sine of 40 right there. That's my sine of 40 on the calculator. Now I want to take this times 12. And we get this, 7.713-ish. So I'm going to say A is approximately 7.713-ish centimeters. Now, going back to solving things, it says find all angular measurements, find all side lengths, draw a picture, make an organizer, and fill out what you know. The thing here is this. When you find an unknown side length, we always want to go back and put it on the picture. I know my picture is getting a little sloppy here, but we always want to go put it back on the image, and we want to use proper units, but we want to ask ourselves, is this reasonable? And one thing I want to point out here is this. Angle A is smaller than angle B is smaller than angle C in this image. Notice that A is 40, B is 50, and C is 90. We could also say then it must follow that side length A is less than side length B is less than side length C, because look, if C is the largest angle, then it has to have the longest side opposite it. So the one thing I want to point out here is basically this. You notice that A is the smallest of the three angles, and this side length is going to be the shortest of our three side lengths because it is opposite the smallest angle. So now the thing we need to finish up with here is going back and solving for B. And I guess at this point we know two sides of a right triangle. We could use Pythagoras to solve for B, but it is always more exact to use trig ratios. So now here's the question again. How could I use this 40-degree angle and this 12 centimeter side length to find this unknown B? How could I relate the 40 degrees to B and this 12? And so what we could say is we could use cosine, because again, cosine, ka, is adjacent over hypotenuse. So now we can set up this equation. The sine, the cosine of 40 degrees. You can see our 40-degree angle on our triangle here is equal to adjacent over hypotenuse. And our adjacent side length here is B, and our hypotenuse is 12 centimeters. So now again, multiplying both sides by 12, then we get this. 12 cosine of 40 degrees is equal to B. So now all we need to do is evaluate this on a calculator. So we have cosine of 40, so 40 cosine times 12. And we end up with this 9.193-ish. So we say B is approximately 9.913-ish centimeters. You notice that I use this little squiggly here that means approximately equal to. We want to go put this up here and ask if it's reasonable, 9.913 centimeters. It seems to be an intermediate length between 7.713 and 12, and that was opposite the intermediate angle, so this seems reasonable. So this is how we solve for unknowns in right triangles using SOHCAHTOA and properties of angles. Cheers.